All right, next example here, we've got sine of 7x over sine of 3x, and we're taking the limit of this expression as x goes to 0. So again, if we just try to plug in 0, like we should always attempt to do at first, unless we are really certain we know what we're doing and what is about to happen. But if we plug this in, we see that we're going to go ahead and get 0 over 0. So in this section is titled Trigonometric Limits, because in all of these limits, all these examples that we have looked at, they all involve a trig function of some kind. And the methods that we've learned previously for evaluating limits not using numerics and not just relying on a graph, sort of like factoring and canceling, the method of the conjugate, none of those things really work here. So in this section, we presented two tools. I mean, the squeeze theorem, and then really these two additional limit facts that will help us evaluate some of these trickier limits. So the technique for this one here is that we want to try to build these two results, sort of get them to appear by rewriting things. So what we're going to go ahead and do here is rewrite this limit, but when I rewrite it, I'm going to put the sine of 7x by itself on a fraction, and I'm going to put the sine of 3x by itself in the denominator of a fraction. So I could just put 1s here for now, and notice that if we multiply, right, two fractions multiplied together, we just do top times the top, bottom times the bottom. So we are allowed to take this fraction and rewrite it in this way, which is sort of like the multiplication of two distinct fractions. Instead of putting 1s here, though, I'm just going to write something else for now. But if it helps you, you can write a 1 there if you'd like. So in order to use these limits, these limit results up here from Theorem 2, we have to have things perfectly matching. So this is saying whatever we're taking the sine of, that same thing has to be in the bottom. And that's the thing that has to go to 0. Okay? So here we have the sine of 7x. That means I need a 7x in the bottom. But hey, we know that we're not allowed to just put something in the bottom that wasn't there before, right? That means I'm going to have to sort of counterbalance. I have to keep things balanced. So if I create this 7x, I'm going to have to also create its, its its anti-particle pair or something like that. I have to make sure I do the opposite. So if I'm going to divide by 7x, I'm going to multiply by 7x. That way, at the end of the day, they cancel. So I still get 1. So similarly, over here, we've got 3x within the sign. So we're going to have a 3x here. And if I create a 3x by multiplication, I'm going to have to do its opposite by placing a 1 over 3x elsewhere, so that they cancel and that whole thing is effectively nothing. So the whole point of this is to try to build these two expressions here. This stuff here is sort of the leftovers. They are the consequences of what we did to create those two things. Okay. So now there's one little thing that I want to mention here. So you can see that theta's here, theta's here, theta's here. So everything in these three areas, they are exactly the same quantity, which is not quite what we have here. Because if you look at this first fraction in isolation, we have a 7x, and then we're taking the limit as x goes to 0. It's not as 7x goes to 0, though. So this doesn't exactly match up here, which is fine. So what I'm going to do here is give us a little like fact over here. So let k be a positive real number. Okay. Then the limit as x goes to 0 of sine of kx all over kx equals 1. We don't actually need this to match exactly for this one. Why is that? Let's prove it. So what we're going to do here is let theta equal kx. Then, so this is a change of variable. Then, as x goes to 0, so let's rewrite this a little bit differently. Let's say, then if x goes to 0, then kx also goes to 0. Right? If x goes to 0, then multiplying that something by a constant doesn't change that fact. It still goes to 0. So, therefore, since kx is just equal to theta, that means theta goes to 0. So in other words, as x goes to 0, that forces theta to go to 0. So what I could do here is I could introduce a substitution. I could just say, let kx equal theta. And then this limit would look exactly like this. Exactly like this. So this limit can, by a change of variable, be morphed into the result we have from the theorem. So really we just need these two things to match. This doesn't have to match exactly. Okay. So with that being said, what happens over here? Well, over here, we can simplify things. We know how to evaluate the limit of this term. We know how to evaluate the limit of this term. This term we know how to evaluate the limit of as well because we can cancel those x's actually. So, the limit of this first term is just 1. The limit of this second term is just 1. And the limit of this term is just 7/3. So the answer to our limit is 1 times 7/3. So the answer to this limit is just 7/3.